So just a real quick couple minutes on the role of a materials testing laboratory. I think a lot of people know what our general role is on a lot of construction projects, you know, where we're doing quality control or quality assurance testing for contractors or owners or engineers, construction managers. But there's a lot of other things we can do also. You know, top left corner there, there's looks like some pavement failure. You know, we can sample the asphalt, sample the subgrade, you know, see what the subgrade consistency is. You know, maybe you got soft subgrade that's causing some failure in pavement. Bottom left corner there, that's you know, making some cylinders. It's you know, kind of an everyday thing for us on a lot of our projects. That middle picture there on the bottom row, we're setting up a seismograph to monitor some vibrations during demolition in another area of the building where we're setting up the seismograph. And that seismograph it's fully automated. It records 24/7 when values get above a certain level. You know, email starts going off and text start flying around. So, you know, there's less chance for harm for the structure. And then the two pictures on the right there, top right and bottom right, we do petrographic analysis. You know, we take concrete, look at it under microscope slides, and you know, see what we can see. You can see in that that top right photo, you know, the biggest difference between that and the bottom one is the air content. You can see a lot more air bubbles in that one in the top right than on the bottom right. Sometimes you want a lot of air in your concrete, or sometimes you want a certain amount. I shouldn't say a lot, but sometimes you want a certain amount of air in your concrete. Sometimes you don't. So a lot of different things we can do to support engineers and other people in the construction industry. But today, we're going to talk about the engineering significance of different tests that we perform on concrete aggregates. I'm going to talk first part. There's going to be a lot of definitions on mostly on concrete aggregates. A lot of the definitions come out of ASTM C125. Some of the definitions come out of ACI 228. I think it's important for us engineers. We're always communicating amongst each other, but sometimes we communicate with others that might not be engineers or architects or in the industry. And I think it's important that we're always talking the same language. So that's why I've got some of these definitions in there, and some of my other presentations that I do. I talk a lot about definitions, again, just to kind of make sure we're all talking the same language. We'll talk about aggregate properties and performance. There's property tests, performance tests. Going to talk a little bit about both of them. Going to focus a lot more on the performance testing, obviously, but we'll touch on some of the property tests. And then there at the end, I'm going to talk a little bit about ASTM C295, which is petrographic examination of aggregates, and how you know, a lot of people think it's an expensive test, but it might be a more economical way. You know, if you've got an aggregate source and you're not sure if it's going to qualify or not, petrographic examination might be an economical way to kind of get a little snapshot on you know, whether or not that aggregate might perform well or not. So definitions, aggregate, I've said that word probably a dozen times already. I think we all kind of know what it is, but you know, here's the definition right out of ASTM C125. Granular material can be sand, stone, gravel, crushed stone, can be slag. Sometimes they'll put slag in there, maybe as a lightweight aggregate, but it's always part of a cementing medium, you know, which is usually hydraulic or Portland cement. Sand, again, we all know what sand is. Pictures there at the bottom. ASTM defines it as, you know, fine aggregate. It can be from natural disintegration. It can be a natural sand. It can be a manufactured sand. Natural sands are getting more and more scarce in some areas. So we're starting to see more manufactured sands than natural sands. Gravel, ASTM does distinguish gravel. Typically, it's a coarse aggregate that has undergone some sort of natural weathering or disintegration or abrasion. You know, some people might call it river stone or something like that, but it's usually identified from rounded corners and edges and things like that, like you see in the pictures there. And then there's crushed stone, which is a product of you know, crushing a larger rock, boulder, cobblestones into smaller fragments. You see those pictures there. I mean, that's probably the, you know, most commonly used coarse aggregate, at least in our area. Although you do see some of the natural gravels. But the crushed stone is pretty readily identifiable just by looking at, you know, based on angularity, and you know, a lot of times the color is all very similar sizes, similar textures, things like that. A couple more definitions. Absorption. Basically, you know, aggregates, they've got permeable pores, and moisture can get into those permeable pores, and that process is just absorption. Density, we prefer the term density over unit weight. It's really just mass per unit volume, you know, pounds per cubic feet, you know, grams per cubic centimeter, something like that. A lot of times you might see some modifiers used with density that might give you a little bit more information on how that density was calculated, or what's included in that density, oven dry density, saturated surface dry density, things like that. Bulk density is really just mass per unit volume that includes all the individual particles and all the voids in between the particles. So if you think of a gallon jar, you throw a bunch of stone in a gallon jar, you weigh the gallon jar, not including the weight of the empty jar, you figure out mass per volume, you know, whatever that mass is per gallon, that's your bulk density. Relative density is really just that, the ratio of density to that of water, you know, so it's really just a specific gravity. Some of the modifiers that we use, absolute density, that includes all the solid portion of the material only. Apparent density includes the solid portion plus impermeable pores within the material. Some delimiting terms that are used when permeable pores are included in the volume. Oven dry density, that's just you stick the aggregate, coarse fine aggregate, whatever, stick it in the oven, dry it back to constant mass so there's no moisture left in it. That's your oven dry density. And your saturated surface dry density, which is probably the most common term that's used in the concrete industry. That's a condition where you've got all the permeable pores are filled with water after it's been submerged, but there's no free water on the outside surface. So it kind of might look damp, but there's no water dripping off of it. And all those little microscopic pores, they're kind of filled with water. And one of the reasons why we use the saturated surface dry density term is because with concrete aggregates, whatever moisture is absorbed into the aggregate in those pores, that moisture is not available to hydrate the cement. So we don't count that moisture as part of the free moisture in concrete when we're doing those types of calculations. Some other definitions, this one's out of the ACI 228 document. Scaling, just kind of the local flaking, peeling away of your paste at the surface. If you look in this picture, there's a lot of things going on here, but what we're looking at is this area right here, the scaling where that paste is kind of flaked off. We've got some efflorescence and some other things, and maybe there's some deeper spalls on the other side, but you see, looking at the side profile here, it's just really this thin you know, that thin outer layer. More starts to come off, coarse aggregate starts to come off, things like that, and it's probably, you know, I'd probably call it more of a spall than scaling. But this picture here would shows what I would consider to be scaling, probably due to freeze thaw distress. A spall is a little bit bigger, flat, circular, oval shaped. You know, it's detached from the concrete, either detached by force, impact, weathering action, internal pressure, fire, things like that. These pictures on the right, these are, you know, this spall is most likely caused by the corrosion of this reinforcing steel, which is an expansive reaction. You know, when the reinforcing steel corrodes, it's expansive reaction and causes internal stresses and pressures, and those near surface, you know, those bars that are near the surface, they just pop the concrete off. A pop out, whoops, a pop out is breaking away of a small portion of the concrete surface, typically due to some sort of internal pressure. A lot of times it's because of pressure within the aggregate. A lot of times it's the coarse aggregate. These pop outs, they're typically like a conical depression, and you can usually see a piece of aggregate right at the bottom of that depression. You can see all these here, all of these pop outs, and these are all due to just poor quality aggregate. We'll see some more of that aggregate here shortly. Delamination, separation along a plane parallel to the surface. It's not a removal. So in this picture on top here, this area, this is a spall, but adjacent to this area, these are all delaminations. You can kind of see the crack right here. So it's delaminating. It's still attached, so it hasn't spalled off. But it's a surface defect. It's a delamination. You know, here's some delaminations here. There's a spall right here. You know, and a lot of times spalls and delaminations go hand in hand. So aggregate properties and performance. Aggregate properties, you know, properties are typically physical: size, absorption, porosity, angularity, density. You know, they're measurable, and kind of physical. You can see it. Performance is a little bit different. Performance can be strength, durability, impact resistance, freeze thaw, weathering resistance, alkali silica resistance. All those are performance properties, and a lot of times these performance properties are directly related to the aggregate properties. So if you've got certain, you know, like say you've got an aggregate with high absorption, it might give you poor performance in, say, the freeze thaw resistance, because it absorbs moisture. That moisture freezes and kind of disintegrates that aggregate, which is actually what happened with those pop outs that we saw on a previous photo. So again, those, you know, aggregate properties could drive towards good or bad performance, and the good or bad performance is oftentimes related to an aggregate property. We do tests on both aggregate properties and aggregate performance tests. You know, again, this presentation is going to be more geared towards a performance test rather than those property tests. And the performance tests, we're typically trying to simulate some sort of external environment or condition that the aggregate, or eventually the concrete, is going to be exposed to, whether it's freeze thaw, you know, impact. You know, maybe it's an internal environment to the concrete where, you know, alkali silica reactivity might come into play. But again, we're trying to simulate some sort of environment that the aggregate's going to be exposed to. So here's a handful of different aggregate performance tests. A lot of these are referenced in ASTM C33, which is a specification for concrete aggregates. C123 lightweight particles, C142 clay lumps and friables. I'll talk about each one of these individually. Some of them I'll spend a little bit more time on than others. So lightweight particles, that's ASTM C123, pretty easy test. It's just kind of a sink float test using a heavy liquid. We don't use water, we use a heavy liquid that's got a specific gravity above 1, right? Again, the specific gravity of water is 1 by definition. So we just put the aggregates in a vessel, and we kind of pick out the ones that that float to the top. And there's the specifications usually allow a certain percentage of lightweight particles, although usually not much. This test is not appropriate or is not done on aggregates that are covered by ASTM C330, which is the specification for lightweight aggregates for concrete. So, think of your, Solite and all of those lightweight aggregates, the expanded shale aggregates that are used, that this test is not performed on those. And I think it's easy to understand why you don't want lightweight particles in your concrete. You don't want them to float. A lot of times lightweight particles, they're lightweight because they're porous, they've got voids, and they're just generally not very durable to be put in concrete. This is actually all one single sample. Some of it's washed up here, and this is actually the aggregate that was used in that that freeze thaw sample that we saw that had all the pop outs. It's lightweight. Not all of these aggregate particles are lightweight, but there's quite a few of them that were, and there were enough to where it had a negative impact on the concrete. Clay lumps and friable particles, also pretty easy test. We're just looking for clay lumps, friable particles, those soft particles. We don't want those in our concrete because we want our concrete to be durable, right? We don't want, clay lumps are going to break down very easily. Friable particles are going to break down very easy. And, typically we don't want our concrete breaking down because of the stuff that we made it with. So we want to keep all this stuff out of our concrete as much as possible. Although it does allow, a certain percentage of clay lumps and particles, 3%, 3% by mass in your fine aggregate. Yeah, generally speaking, we don't want to see any of this stuff in there. ASTM C88, magnesium and sodium sulfate soundness. This is a really popular test that we do. It's a cyclical test, kind of a wetting, drying, and it's done in either magnesium sulfate or sodium sulfate. It's usually specified by the user, the engineer. It's in the project specifications. I think New York State DOT, for the most part, uses only magnesium sulfate. And how this test works, again, it's kind of a wetting, drying, where we take the samples in these stainless steel baskets, and we submerge them in a magnesium sulfate or sodium sulfate solution that's got a defined specific gravity, so we know the concentration. It's a given concentration. So you soak it in that, and then you take it out, and then you put it in an oven to dry out, and as it's drying, the salts crystallize, and the solution gets in the pores. Remember, there's the absorption test. So there's these aggregates have some absorptive property. So the solution gets into the pores, and then as it crystallizes, that crystallization creates an internal pressure that kind of simulates freezing and thawing. So this test at the end of the day is kind of a mass loss. So we do the soaking, drying, weigh it before, weigh it after, and hopefully there's not a lot of loss of material. ASTM C131 is the LA abrasion, Los Angeles abrasion, and it simulates degradation by impact. So we've got all these steel balls, 6 to 12 steel balls, are all about 1 pound or about the size of a golf ball. and they're put in this rotating drum along with the sample. It undergoes a certain number of revolutions. There's a revolution counter right here on the machine, so it goes through a certain number of revolutions, and then we weigh it, or actually we run a gradation on it before it goes in there, and then we run a gradation on it afterwards, and we see how much of the material was broken down. There's no mass loss, right? We're not losing any mass, just the particle sizes are breaking down. It can be a pretty extreme test, with all these steel balls rolling around, beating off of the aggregate. But ASTM does allow you up to 50% maximum degradation, so you can have quite a bit of degradation. But again, this test is tests impact, abrasion resistance. If we're using it on roads, highways, bridges, things like that, it needs to withstand a certain amount of abrasion, whether it's vehicles kind of coming around a corner like this, kind of a steep corner, whether there's accidents that happen, up here in the Northeast, obviously, hopefully not so much anymore. We're getting out of that season, but plow trucks, those plow blades, obviously they're creating a lot of abrasion on the roadways. So, and the LA abrasion test is not just unique to concrete. Also, we do it for asphalt as well, for obvious reasons. Next test, ASTM C666. That's the resistance of concrete to rapid freezing and thawing, and I've got concrete underlined there because it's not a test that's done just on the aggregate itself. A lot of these other tests are, the aggregate's isolated, and we're testing the aggregate. Here we're testing, a concrete, the whole concrete matrix with the aggregate in it. Typically done on cast or saw cut beams. There's two different procedures. There's an A procedure and a B procedure. Procedure A is probably done, I'll say 95% of the time, where it's both, you're both freezing and thawing your sample in water. Procedure B freezes it in air and thaws it in water. The test method is 300 cycles, so it's quite a few cycles, freezing, thawing, freezing, thawing. And internal effects can be quantitatively evaluated by testing the fundamental frequency every 36 cycles. As I said, the test is done on concrete, and it evaluates not just the aggregate durability within the concrete, but also the air void structure. So when using this test, and I think FAA and Army Corps both specify this test for concrete pavements, when doing this test, you use the aggregate that's specified, because it is in FAA and Army Corps. I believe it's an aggregate test. But you make up concrete, you make up freeze thaw durable concrete that's got air entraining agent in it, and then you do the freeze thaw test to see if you get any pop outs, essentially, like we saw in that other sample. I mentioned it kind of quantitatively evaluates it internally, and it's kind of neat how it does it. So part of the test method in ASTM C666, they reference this other test method, ASTM C215, where we're testing the fundamental frequency and the longitudinal, transverse, and torsional directions, where we set up in the longitudinal direction, we put an accelerometer on one side and we strike it with a hammer on the other side, and you get a wave that travels through the concrete, and we figure out, we do some calculations and figure out what the fundamental frequency of that material is. When we do it in this configuration, that gives us the longitudinal. When we do it in this configuration where we have the accelerometer on one side, we do a hammer strike right in the middle, and it kind of bounces off, kind of in the short direction. I'll say, that's the transverse direction. That gives us the transverse fundamental frequency. And then we don't do this as often, but sometimes we'll do it. This is the torsional one, where you put the accelerometer kind of down in the bottom left-hand corner, and then we do a hammer strike in the top right-hand corner, and it kind of, you know, creates this twisting motion. And how we evaluate it quantitatively is we just figure out, we do all these tests before we start any of the freeze thaw cycles. That gives us our N sub 0 value. That's our initial fundamental frequency at zero cycles. And then every 36 cycles, we take it out, we run these tests, and then we just figure out what the ratio is of, you know, those fundamental frequencies at those cycles versus the initial fundamental frequency. And as it changes, as that fundamental frequency changes as you're going through the freeze thaw action, it tells us that something is changing inside the concrete. So we know there's not only visual things that we can see on the outside. Here's that same lightweight aggregate in here. We can see there's obviously there's scaling, there's spalling, there's pop outs, there's all kinds of things going on in this sample. But again, in this condition or this particular case, we were testing the aggregate, you know, the durability of the aggregate to be used in concrete. So we're testing the whole concrete sample, and we're seeing how the aggregates are responding. And again, they didn't do so well. Okay, we're going to talk a little bit about alkali silica reactivity. Big deal sometimes. Some people call it concrete cancer. Basically, it's when you've got the materials inside your concrete are not getting along very well. So you've got this ASR gel that's formed, and you need these three materials. You've got your here's your silica, right, in the form of quartz. Here's your water. You know, that's pretty much in every concrete. And here's your alkali, sodium hydroxide in this case. Add all of these together, and you get this gel. And the gel is volumetrically larger than the materials that make up, you know, than the reactants. So it's an expansive reaction, and similar to reinforcing steel when it's corroding, which is an expansive reaction and causes, you know, tensile stresses and things like that around the reinforcement. Same thing, it's an expansive reaction, causes tensile forces around the aggregates, and can be detrimental to your aggregate. So in this picture here on the right, we kind of see this plug of ASR gel in this piece of coarse aggregate that's kind of squeezing out, and you can see this crack right here that's forming because of that. Once ASR starts, usually it continues as long as all three of these are still available. It's kind of like the fire. You know, if you think of the fire triangle, you know, you got a fire. If you remove one of those three elements from the fire triangle, the fire goes away. Kind of the same thing with ASR. If you can remove one of these three elements, it'll go away. Probably the easiest one to remove would be water, and this water is external water. So we typically only see ASR distress in those, you know, exterior concrete that's exposed to water, and a lot of times it's the wetting and drying process that kind of exacerbates it. And all of these pictures are from the Federal Highway ASR AAR handbook, but these two here on the top are pretty interesting. And we can see this kind of typical map cracking that we see with ASR. Now, I'll tell you that not all map cracking is due to ASR, but that's, you know, ASR typically does cause this map cracking. But you can see this is a bridge abutment, and you can see this backfill line right here. So everything below this line was covered with soil. So yeah, it might have been exposed to water, but it wasn't exposed to as much water. So you can see there's not, we don't see all of that map cracking distress down here like we do up here. And here's a picture of that interface. Yeah, there's a little bit of cracking here, but certainly not as much as you've got where all that wetting and drying is occurring. So again, kind of keeping the water out is probably the most effective way. Well, most effective way is to make sure that you've got aggregates that aren't susceptible to ASR. But once you've got it, it's hard to deal with a lot of times. So some general ASR test conditions. The test simulates a high alkali environment. That's the alkalis are supplied by the cement in the concrete, but during our test, we typically use sodium hydroxide, which can be pretty nasty stuff. We put metal studs, we cast those right into the specimen. We take length measurements at regular intervals. Obviously, we check the length before we start the test. We soak it in sodium hydroxide or some other hydroxyl alkali solution, and we measure expansion over time. All ASR tests can experience false positives and false negatives. Extending the test duration can help to cut down on the false negatives, but it doesn't necessarily do anything for the false positives. There's a lot of different ASR tests out there. Some of them give more false positive negatives than others. But I'll talk about some of the different tests. But all of the ASR tests involve length change measurements. This is the device that we use. This is a sample right here. It's a one inch by 1 inch mortar bar, and we've got it in our measuring device. This measures the relative length. So it's this 0.3206. This whole sample is not that length. That's just the relative length change. But we take these measurements out to the 10,000th of an inch, which is that's a pretty small length. But we use the same device, whether it's a 1 inch mortar bar or a 4x4 inch 4x4 inch prism, which we see here. Use the same tools, and we take all the measurements out to 10,000th of an inch. So ASTM C1260, probably the most common ASR test. Some people call it the quick test. Some people call it the mortar bar test. It's got a bunch of different names to it, but the test itself, 16 days. We're soaking the sample itself, so that that 1 inch mortar bar, we soak that in sodium hydroxide for 14 days. And the test evaluates coarse and fine aggregates separately. So if you've got a fine aggregate that you want tested, we mix it up with 1 part cement and 2 1/4 parts graded aggregate. So we grade the aggregate, the fine aggregate, so the gradation is the same for every sample. And the water cement ratio is the same for every sample. So there's a lot of, it's a standardized test. When we do it on coarse aggregate, what we have to do is we have to take that coarse aggregate, whether it's gravel or crushed stone, we've got to crush that down to a graded sand. So that sand gradation, again, is the same whether you're using fine aggregate or coarse aggregate. You just crush down the coarse aggregate to get that graded sand, mix it with 2 1/4 parts of the aggregate, 1 part cement, and a water cement ratio of 0.47. ASTM C1567 is, for the most part, it's the exact same test method. Procedurally, it's the same, testing coarse and fine aggregates differently, crushing down the coarse aggregate to make a sand. The biggest difference is you're replacing the cement with some other cementitious material, fly ash, silica fume, slag, something like that. and that's used to check to see how well the fly ash, silica fume slag, whatever, how well that is mitigating the ASR expansion. Fly ash, silica fume slag, they all do a pretty good job of mitigating ASR, which is why you see a lot of the state mixes have got 20%, 25% fly ash in it. Sometimes there's restrictions where you have to put in some sort of pozzolan like fly ash. So after the test is done, we produce a graph like this. Again, it's soaked in the solution for 14 days. We take it out every now and then, and we take measurements on it. This is the length change as a percent of the starting length. And ASTM C1260 tells us that length changes below 0.1% are typically innocuous. That's this green line here. So anything below the green line is typically good. In between the green line and red line, between 0.1 and 0.2% length change, they recommend additional testing. And that may be extending the test method out or doing some other test, maybe petrographic analysis or something like that. And then it states that any expansion over 0.2% is considered potentially deleterious. So as we look at this this graph right here, here's our length change up to 14 days. We're well below 0.1. This would be considered innocuous. This sample, not so much. Again, here's our 14 days. We had almost 0.25% expansion after 14 days. So this would not be good. There's another test method. As I said, there's a handful of different ASTM test methods for alkali silica reaction. This particular one, ASTM C1293. This one's a little bit unique in that you have a fixed alkali content, and that alkali content in the mix is 5.25 kilograms per cubic meter, or 1.25% sodium hydroxide by mass of cement. So every test, every aggregate has the same amount of alkali content in it. And to get to this 5.25 kilograms per cubic meter, a lot of times, well, every time, you have to add sodium hydroxide to the mix water. Remember, sodium hydroxide, that's your alkali solution. So you're actually mixing that in with the concrete, mixing it in with the water. You're not soaking it in this sodium hydroxide solution. You're actually mixing it in with the concrete. Coarse aggregates are tested with non-reactive fine aggregates. So if you think back to that first graph that I showed where that aggregate was 0.05% expansion, we could use that aggregate, assuming it was fine aggregate or coarse aggregate, we could use that that aggregate in our test with the other aggregate that we're testing to evaluate. So for coarse aggregate, we use non-reactive fine aggregates. If we're testing fine aggregate, we're using non-reactive coarse aggregates. And again, those non-reactive aggregates, they should be tested to prove that they're non-reactive. The amount of cement in each mix, 420 kilograms per cubic meter. It specifies ASTM C150 cement with a total alkali content of 0.9. And again, you're adding sodium hydroxide to raise that alkali content. Here's the bad part. The test duration is 12 months. Sometimes it's longer. If you've got a certain amount of expansion, they recommend carrying it out to 18 months. If you've got a project that's bidding in a month or two, this could put you behind the 8 ball a little bit if they're specifying this test. So this test is quickly becoming the preferred test because it does seem to have fewer false positives and fewer false negatives. But again, it's a 12-month test at least, so it's not great as far as scheduling goes. We're going to talk a little bit about alkali carbonate reactivity. This is it's hard to put our fingers on. Most people think it's due to the dolomite in carbonate aggregates. Some people are now starting to think that it's just kind of a different form of alkali silica reactivity, but kind of similar in the sense that you've got a carbonate material. In this case, it's dolomite reacting with the sodium hydroxide that forms, some sort of, some other reactant that is also expansive. This dolomite particles are usually identified by these rhombus or rhomboid shaped crystals within the aggregate. I won't talk about this too much. It's a thing. It's out there here in New York State. Western New York. We do have some dolomitic limestones that could be susceptible to this. That we do test sometimes. Sometimes we look at them petrographically to see, to kind of look for these rhomboid patterns. So ASTM-C 586, alkali reactivity of carbonate rocks. This is a rock cylinder method. This is a test that's done on a very small cylinder, about 1.5 inches tall, maybe 1/3 of an inch in diameter. So it's pretty small. We soak it in sodium hydroxide. We're measuring it at 7, 14, 21, 28 days. And every 4 weeks afterwards. This one also is kind of a long test. It's 12 months or more. But we're looking for the same thing. We're looking for that expansion. We're looking for that, that expansion is caused by the reaction. So we know if things are expanding, as they're exposed to the alkalis, sodium hydroxide in particular, we know if they're expanding, that there's some kind of reaction going on that is probably not going to be welcomed in our concrete. Is going to be detrimental to our concrete. So. But again, this one's a 12-month test also. This is done on a cylinder. It's not done on a like a crushed piece of aggregate. Another alkali carbonate test, ASTM-C 1105 is a prism test where you get a 3-inch by 3-inch by about 11-inch prism. Very similar to ASTM-C 157, the shrinkage test, but you're not immersing it in water. It just uses whatever project cement, whatever the project mix design. You can use reference cement if you're using it for general evaluation and not for a specific mix. And you're looking for expansion. Same thing. You're mixing things up. You cast pins into the sample and then you measure it. We're not soaking it in anything. We're just waiting to see what happens. And then we're taking measurements 3 months, 6 months, and then even take them out to a year or more. So as you can see, these tests, it takes time for the reactions to take place. And once those reactions take place, it kind of takes time for them to manifest into expansion. So again, a lot of these tests, which is probably the reason why that C1260 test, the one that people call the quick test, is the more popular ones, because a lot of these other ones take 12 months or so. So we'll talk a little bit about ASTM-C 295, petrographic examination of aggregates. This is a microscopic examination, of course, in fine aggregates. We're identifying physical characteristics, and remember, a lot of times these physical characteristics, they impact the quality or the performance of the aggregates. So rather than doing a whole bunch of different performance tests, which a lot of times are needed, if you've got an aggregate source, coarse or fine aggregate source, that you're not sure if it's going to be viable or not, maybe the first step is to do petrographic examination rather than, spend what could be $3,000 to $5,000 on all these different performance tests between, ASR and freeze thaw and, some of the other ones. Maybe you do a quick petrographic examination to look at the characteristics, the physical characteristics, to see if any of those physical characteristics are present that might lead to deleterious reactions or poor performance. And we pretty much did this with this aggregate sample here. This is the same sample of concrete that I've showed you. We ran, we did petrographic analysis on this. We identified lots of, lightweight porous aggregate. We recommended that it not get used in concrete production. And we furthered that by, basically making some concrete, doing some freeze thaw tests, and this was the outcome here. So, but anyway, the idea again is rather than go through all the performance tests, maybe do a petrographic examination as a first step to see if some of these other performance tests might be warranted. So that brings us to the end. We'll